Hello friends, today I will discuss the resonance in RLC series circuit. In this topic, I will cover definition of the resonance, impedance variation with the variation of the frequency, and impedance at resonance frequency, impedance at cutoff power frequencies F1 and F2, resonance frequency, bandwidth, lower cutoff frequency, upper cutoff frequency, power factor variation. Let me consider first definition of the resonance. When the applied voltage and current are in phase, then the circuit is said to be in resonance. Let us consider resistance, inductance, capacitance connected in series with the voltage V, AC voltage, and whose frequency can be varied. For this circuit, the impedance of inductance can be written as J omega L. For capacitance, impedance can be written as Zc is equal to minus jXc. Xc is nothing but 1 by omega c. So this is equal to minus j by omega c. Similarly, the impedance of the resistance means Zr. The total impedance of the series RLC circuit can be written as Z, which is equal to Zr plus Zl plus Zc is equal to R plus J omega L minus J by omega c. Rearranging the terms, we get Z is equal to R plus J into omega L minus 1 by omega c. If you see, the variation of the inductance and the capacitance reactances are like this. So when the frequency increases, the inductive reactance will also increase, that is equal to XL is equal to omega L. So which is a linear passing through the origin like this. This is XL on y-axis, frequency variation on x-axis. Similarly, for capacitance, the capacitance reactance is given by 1 by omega c. That means the reactance of the capacitance is inversely proportional to the frequency of the supply. When the frequency of the supply is less, the capacitive reactance is very high like this. As the frequency increases, the capacitive reactance decreases like this. On y-axis, Xc is shown. Similarly, there is a resistance in the circuit. That resistance do not vary with frequency, so it is a constant line parallel to the x-axis like this. This is shown by R here. When we draw the equivalent graph for impedance, then we get the curve like this. So in this region, we find that Xc is more than XL up to here. After this, XL is more than Xc. So that can be seen very clearly like this here. This is the total impedance, and this is the base value is nothing but a resistance Z is equal to R, which is a minimum impedance here, and below the this frequency, this is called the minimum impedance point, is corresponding to the resonance frequency. Below the resonance frequency, the capacitive reactance is more than the inductive reactance, which was seen in the graph also. Here it is more, whereas this is low, 0 almost. Similarly, above the resonance frequency, XL is more than XC. So that's why we can say it is inductive dominating circuit. This side it is capacitive dominating circuit. So the power factor in this region means below the resonance frequency will be leading. So we write here power factor leading. Similarly, above the resonance frequency, we say the power factor is lagging. And the impedance Z is equal to R is called the dynamic impedance at resonance. We know the impedance of RLC series circuit, that is Z is equal to R plus J omega L minus J by omega C. So here we have the real part R and this is the imaginary part. At resonance, imaginary part of Z is equal to 0. That is omega L minus 1 by omega C becomes 0. So from this, we can write omega L is equal to 1 by omega C. So from this, transfer this omega to the left and L to the right side. Then we get here omega square is equal to 1 by LC. And omega we can write is equal to root of 1 by LC or 1 by root LC. This omega is corresponding to the resonance frequency, angular resonance frequency. So when we express this in the form of frequency, we know omega is equal to pi f. So then we can say resonance frequency Fr is equal to 1 by 2 pi root LC. Under resonance condition, the impedance is only a real part of the impedance, that is R. So the current at resonance we can write as V by R and represented by Im. This current is maximum. When current versus frequency curve is drawn, then the curve is obtained like this. And this is the point where the current is maximum, that is nothing but Im, which is equal to V by R. And there are cutoff frequencies, that is half power frequencies, that is here the power is maximum, whereas here half the power that is consumed here, that is Em by 2 occurs when the current in the circuit is equal to Im by root 2, that is this point and this point. When the current is same, then it is called the impedance in the circuit is same at those points, and those corresponding points we call as cutoff frequencies. This is omega 1 is called the lower cutoff frequency, whereas omega 2 is called the upper cutoff frequency, and omega is called the resonance frequency. And the difference of frequency between omega 2 and omega 1, that is omega 2 minus omega 1, is called the bandwidth of the circuit. Let us see the derivation for bandwidth for series RLC circuit. So as seen on the frequency versus current, it can be observed that the impedance at this point and impedance at this point are one and the same. That is ZF1 is equal to ZF2. ZF1 is the impedance at F1, ZF2 is the impedance at F2. So since current is same, so the impedance must be same for a applied voltage which is constant. Then at half power frequency we can say ZF1 is equal to ZF2 is equal to root 2 R, and this can be written as ZF1 is equal to ZF2 is equal to R plus JR. So when we take this magnitude, then we get root 2 into R. Then we can also write like this by squaring the right hand side and left hand side. Then we get like this, r square plus x square is equal to r square plus r square. This z consists of both r and x. So from this we can write x square is equal to r square. So from this x we can write as plus or minus r. At frequency f1, xc is more than xl, and when we write xl minus xc, we write minus r. Similarly, at f2, xl is more than xc, then we write is equal to r from this equation. So that is xl minus xc is equal to minus r. So this happens when frequency is f1, that is omega 1, that is omega 1 L minus 1 by omega 1 C is equal to minus r. And after simplification, we get omega 1 square LC minus 1 is equal to minus r omega 1 C. Then transferring this LC, or dividing the whole equation with LC, then the equation becomes omega 1 square is equal to omega 1 square minus r by L omega 1 minus 1 by LC is equal to 0. So from this, omega 1 can be calculated using the formula called after rewriting this equation, we get omega 1 square plus r by L omega 1 minus 1 by LC is equal to 0. So from this, omega 1 can be written as omega 1 is equal to minus b means minus r by L plus or minus root of b square means r by L whole square minus 4ac minus 4 1 into minus 1 by LC means plus 1 by LC. So here becomes plus 4 by LC and divided by 2a means 2 into 1. Then we get like this. So once 2 is absorbed into this root and here, then we write omega 1 as minus r by 2l plus or minus root of r by 2l whole square plus 4 by 4lc. So this 4 going to get cancelled, and we can write equation like this: omega 1 is equal to minus r by 2l plus or minus root of r by 2l whole square plus 1 by lc. On similar lines, omega 2 can be written as like this: xl minus xc is equal to r. So here omega 2 L minus 1 by omega 2c is equal to plus r. So from this we get omega 2 is equal to r by 2l plus or minus root of r by 2l whole square plus 4 by 4lc. So after further simplification, omega 2 becomes r by 2l plus or minus root of r by 2l whole square plus 1 by lc. And let a is equal to r by 2l and b is equal to root of r by 2l whole square plus 1 by lc. So then omega 1 can be written as minus a plus b. So that is b minus a. Similarly, omega 2 can be written as a plus b. Then omega 1, omega 2 can be written as b minus a into b plus a. So this becomes b square minus a square. And we know what is b and what is a. After further simplification, then we get here 1 by lc. And we know omega r square is equal to 1 by lc, which is derived earlier. Then we can say omega 1 omega 2 is equal to omega r square. So further we can write omega r square is equal to omega 1 omega 2. or omega r is equal to root of omega 1 omega 2. So in other words, in a series RLC circuit, the resonance frequency is geometric mean of omega 1 omega 2. Then bandwidth can be written as omega 2 minus omega 1, that is b plus a minus of b minus a. So after further simplification, bandwidth omega 2 minus omega 1 is equal to 2a, and a is already defined r by 2l. So 2 into r by 2l means that 2 going to get cancelled, then omega 2 minus omega 1 will become r by l. And we know omega is nothing but 2 pi f. So from this we can write frequency is nothing but omega by 2 pi. So that this equation omega 2 minus omega 1 we can write as f2 minus f1 is equal to r by 2 pi l. This is the formula for bandwidth of the series RLC circuit, and quality factor of the circuit can be written as inductive reactance divided by the resistance of the circuit, which is also equal to the reactance of the capacitance divided by resistance of the circuit. This quality factor can also be written as the resonance frequency divided by bandwidth. So resonance frequency can be written as Fr, whereas the bandwidth can be written as F2 minus F1. Substituting the value of Fr and the bandwidth, quality factor will become like this. Resonance frequency can be written as 1 by 2 pi root LC divided by bandwidth means R by 2 pi L. So that 2 pi L going to come to in the numerator, that is 2 pi L. So after further simplification, quality factor will become 1 by R root of L by C. And this quality factor can also be called as the voltage magnification factor, given by voltage across the inductor divided by supply voltage or voltage across the resistor, which is also equal to the voltage across the capacitor divided by the voltage across the resistor, which is equal to the supply voltage. So let me summarize once. In the series RLC circuit at resonance, we have seen what is a definition of the resonance, a variation of the impedance with frequency and resonance frequency, the impedances at half power cutoff frequencies, resonance frequency, bandwidth, lower cutoff frequency, upper cutoff frequency, power factor variation, quality factor, voltage magnification factor, the relation between quality factor and the bandwidth and resonance frequency,